Anyways, if you miss the first day, all you got to do is watch the video, review the lecture notes, if there are any, and there usually are, and if you create a program during the video, upload it to the Dropbox. If you're not able to create a program or whatever we were supposed to do, just fill out the lecture video form. Now let's talk about where we find all of these, because I'm not going to be, writing one of these messages every single day, every single time we have class. So all of that stuff can be found under content, right? Lecture videos, we click content, we see lecture videos. Right now there's only one. I don't have a link to the playlist yet. I'll add one up there so you can just, click on the playlist and find whichever one you want that way, or bookmark the playlist. And daily notes, same idea. Where are you going to upload it? You can upload them by going to assignments, and you'll find the Dropbox, and it'll have the same letter. The homework will always be found in the assignments folder. I'm going to try to do something that I haven't done in the previous 103 classes, which is have the homework also posted to a folder in here. But, right, you'll find the documents here, but you're also always going to find the documents right there in the assignments folder, so you're not going to have to go there for it. It's just going to be convenient, because that way I'll have all the documents in one folder, so that when I port the class to Canvas, it'll all be right there for me. Some people like seeing them all in one place rather than having to go to the assignments folder. Right now there's only one, install Python. So we're going to hit chapter 1. Not a lot of programming involved, so we will rip through it pretty quickly. Oh, one more thing to check out is that just to remind people that they do need to be doing the book quizzes. I'm going to be adding quizzes to MindTap just because they put dates, right? If I come up and I'm viewing this in student mode and, I log into the page, it'll tell me, you haven't done the quiz, right? So that's cool, because otherwise you may not get a reminder of it, because I don't want to go in and set due dates on the quizzes in MindTap and then add them again and then add them again and add them again, because you know that I want you to take them as often as you need to. But the side effect of that is that if you go into Cengage, and you view it by calendar, it's not going to show you that anything's due, right? And last semester I had people just not do stuff in Cengage because I didn't put due dates on it, right? So they got way behind as far as the book was concerned. So I'm trying to make it real clear. That's why the quiz is there. But what is the quiz? All it is a yes/no question. Yeah, I did the quiz, right? So you go here, and it just reminds you. And whenever you get done with it, come back here and mark it's true. It's not really a quiz. If I ever put a quiz out here that is important, it's not just a link to MindTap. I'll make it very clear that you have to do that, right? Because I will be covering material in here that's not in the book. So we'll make two categories. Why don't we do that right now? And this one's just going to be called MindTap Reminders. That's what the category is going to be. These aren't even worth any points in this page. However, in MindTap, they are worth points. They are worth credit. So that's where you get your credit for those quizzes. I hope that's not too confusing. I can explain it again if I need to. I'm not sure if I'm the only instructor who doesn't set due dates on the quizzes so that you can repeat them over and over. Anyways, maybe I'm the only one who lets people do things over and over. I'm not sure about that. So we got some PowerPoints we're going to wade through. Let's hit the PowerPoint for chapter 1. Every textbook always does this. The history of computers, or overview of computers and programming, stuff like that. But this is the fundamentals class. It's worth looking at that stuff. But I know that we pretty much, everybody grew up with a computer in their, in their infant chair and stuff like that. So you pretty much already have the idea of what a computer is. And so there's not going to be any questions on an exam about the difference between hardware and software, right? So what is a computer system? It's a combination of all the components required to process and store data. All right. What is data? It's information. It's like text that you type in, it's pictures you take, it's audio. You know, there's infinite amounts of data. It's anything that can be encoded into like a series of zeros and ones and stored. It's anything that can be put into numbers or numeric data, right? An MP3 is just a series of numbers in a video file. You know, it's just a series of numbers stored behind the screen, and it's up to the application to open that and read it in and then construct it into memory in such a way that it looks pretty to you. And so what is hardware? It's the stuff you can touch. What's software? It's the stuff you can't touch, right? So this is the hardware, and you open it up, you know, and you bash it open, you see all the chips, you know, and the hardware includes a touch screen. The touch screen is an input device. Nowadays it's cool because the input device and the output device are the same thing, right? The screen is both for input and output. It didn't used to be that way for the most part. Yeah. More traditionally, we think of input devices as being the keyboard and the mouse. That's what we're going to interact with. You could have all sorts of input devices. Some people like tablets, you know, scanners, that kind of stuff, microphones, cameras. So the software are the instructions that tell the hardware what to do. And using those instructions, people create programs. And there's all sorts of different categorizations of programs. There's like system software and operating system software. That's all the stuff that just controls the computer, right? You know, every time you turn the computer on, it loads those programs up, right? And then there's applications, right? The applications are the stuff you launch because you want to do something. You want to create a document, or you want to play a game, or you know, you want to get on the internet or something like that. So what is the art of programming? It's writing software instructions. And just because I'm going over this pretty fast doesn't mean that when you take the Chapter 1 quiz, you know, you're not supposed to remember this, but you're going to be able to go through, you know, the book. Just open up Cengage in 2 windows, right? I think it'll let you do that. You know, one for reading the text, one for taking a quiz, and scroll through the text until you find the answer. You know, that way. Hit the PowerPoint, right? You ought to be able to go through it pretty quickly. And the only reason I'm going through it quickly is because I know that we already all know what hardware is. Stuff like that. So applications are word processing. And system software is the operating system. And then sitting on top of the system software is kind of the nebulous middle ground, which are the utilities, right? The utilities. I'm going to format my hard drive. I launch something that lets me format the hard drive, or something that will configure my video driver or stuff like that. You don't really think of that as an application because you're not creating documents and stuff, but ultimately it is. Ultimately, all of these are just programs. All right, now we're getting into some good stuff. What do programs do? Generally, they do 3 things, ultimately. Whether a video game or an Excel spreadsheet or anything, they get input. They do processing on that input. And then they display output. Now, there's certain circumstances where you may write a program that doesn't take any input, right? If you're going to calculate the value of pi, it probably really doesn't need to ask for any input. It's just going to go and calculate the value of pi. On the other hand, we know that pi is like an infinite number, right? So it might ask you, you know, how many digits do you want to calculate pi out to? In that case, it would be getting input. Or, you know, you have a program you run and all it does is display pretty pictures, right? You know, all it does is draw a design on the screen. And people don't use screensavers anymore pretty much, but that's the same kind of thing. But even screensavers had to respond to input, right? You wag out your mouse, the screensaver would stop. So they had to accept input. Video games. Video games are constantly accepting input, right? You're moving your mouse, you're touching your screen, you're typing keyboard commands in. So these run in a cycle quite often. But we may be getting some input, doing some processing, displaying some output. Getting more input, doing some more processing, displaying some output. Like Word is sitting there waiting for you to do some input. And you type in a letter, and it modifies the document in its brain, right, in its memory. That's the processing part, and it puts that letter on the screen, makes a change on the screen. That's the output, and it keeps looping over and over. Video games, right? You know, you keep touching, that changes something. That's the processing. It changes its internal variables, and then it updates the display. You know, and then when your game freezes and it's no longer updating the display, you get really annoyed. our programs are going to tend to, at the very, very beginning, just get some input, just do some processing, and just do some output. Right. Run, calculate, somebody's whatever, credit rating or whatever based on some information, who knows, and then display that, and then it's done. But really, programs usually loop over and over and over, so we will be adding loops to it. So, you run the program and you figure out, your whatever, your weight in kilograms by typing in pounds. It'd be nice if it ran again. And you kind of probably have seen anything, do you wish to play again, right? Or do you wish to repeat, or whatever. That way, when the thing is done, it can run again. And we will be doing that. So the third step here will be the output, even though we don't see it here. It's on the next slide. The resulting information is displayed, however so. Might be on a monitor, it might be saved to disk, sent to a printer. People don't really send stuff to printers very much anymore. A cloud-based device is accessed through the internet. That just means that the program is stored on the internet, and so when you're ready to run it, it has to download the program, and then the data is uploaded back to the internet. All right, programming languages. There's all sorts. There's hundreds of programming languages. If you Google up, wiki programming languages, list of programming languages, so anyways, you get the idea. There's a billion of them. Each one is tailored for a different task. Some of them are very specialized. Some of them are joke languages created because a programmer thought it was a funny thing to do, and they try to write a deliberately difficult language or whatever. They're designed for different reasons. Python is written to be a very useful language with a pretty simple syntax, so that you can write a program in just a couple of lines and it'll be useful. And also so it'll be run on multiple platforms. Platforms of things like Macintosh, Windows, Android, Linux and stuff like that. How does it do that, right? Some programs don't run on multiple platforms, right? If I have Word on my Windows machine, that doesn't mean that I can copy those files, or that executable, that program on my Mac and have it work, or copy it onto my phone or have it to work. They have to write separate programs to work on each platform, right? So they hire, Android developers to write a Word version for Android or whatever. I'm not sure there is. I'm probably sure there is, and then iOS. And, there's going to be a Mac version of Word. But they have to have separate teams of programmers writing it for each one. It'd be cool if you could write a program just once and have it magically work on all those platforms. Like if you spend $1 billion writing, Call of Duty for, the PlayStation, it'd be really neat if you could just publish it and work on the Xbox as well. PlayStation wouldn't be happy about that. They want you to only buy software for them and kind of lock it in. But, the idea of a multiple platform software is that you can write something once and it'll run on multiple kinds of computers. Well, how does it do that? If I do this isn't really work very well. The glare may be blinding. I apologize for that. Maybe it'll be okay. I don't usually write on the board very much. What happens is, you have some code, and then when you try to run the program, it runs on a second layer, which in some cases we could say is an emulator. And I'm sure that a lot of y'all are familiar with the idea of emulators because you want to play like old Nintendo games on your PC or on your phone or whatever, right? Old video games, stuff like that. That's a really common use of an emulator program. So what the emulator does is it's just another program, but it pretends, it mimics the function of all the chips of the Nintendo or whatever it's supposed to be doing. And so you just give it a file that was copied straight from a Nintendo cartridge, and it knows what to do with it. And it interacts with it in the format that specific thing needs, right? It needs to be able to display to a screen. It needs to be able to accept input. Now, the way that input-output, and the hardware of that machine, these things differ dramatically. The way that works on Android is completely different than the way it works on iOS. So you write different emulators for each one. And so, you know, Windows is going to have emulators. And people love their old-fashioned games, their retro games, their PlayStation 1 games, and they want to be able to play it on multiple devices. So the same code, the same zeros and ones, the same numbers, can then run on Android or iOS or Windows or anything that that emulator has been written for. You know, I've even seen videos of, like, you know, printers with a little LCD screen, and people are playing Doom, or they've written Doom in such a way that it runs on the printer, which is ridiculous, right? But it's actually just the same Doom that you would have installed on your Windows in the 90s. It's just that somebody wrote an emulator program that you could install on your printer so that it would run Doom. And because the people who wrote Doom published the code to the internet so that everybody could run it. Anyways, when you're talking about programming languages, it's not called an emulator because it's not emulating hardware, but it is talking to hardware. So it's still got the hardware right down here, you know, and it's still getting input and output, stuff like that. But it's called an interpreter or a runtime engine. Maybe you've heard that term, right? And so it takes the Python code and it works with the custom hardware of the Mac, or it works with the custom hardware of the PC or whatever, so that even though this program is different, the code we write is the same. And that's not magical to Python. Java works that way. JavaScript works that way. A lot of programs, languages nowadays, have that functionality. There are some programming languages that are designed to run with an interpreter or a runtime engine. Those are the ones where you want to run your code really fast. Maximal speed, maximal performance. For that kind of stuff, you want to program as close to the metal as possible, right? You don't want anything sitting between your code, your program, and the hardware, right? Because you're trying to update the PlayStation screen 60 times per second so that, you know, it looks as fluid as possible or whatever. So video games are not usually written in Python, or Java or stuff like that, because this step does slow it down, right? Doesn't mean you can't write games. You know, you certainly can write games, but they're not going to be the high performance games, right? Where, you know, you're trying to get the maximum frames per second or whatever. You know, if you're playing, Candy Crush or something like that, you know, the performance isn't as important as when you're playing the shooters, you know, where you're trying to, get as much stuff going on as possible. Nowadays, interpreters are really getting pretty good. The one called JavaScript used to be incredibly slow and kludgy, and then there was kind of an arms race between Apple and Google and Microsoft to develop the best versions of JavaScript, and now JavaScript runs amazingly fast. So you can play a lot of games now in your browser that are purely JavaScript based because it's fast enough. But still, it's not fast enough for Call of Duty or whatever the most popular awesome game is now. Fortnite? Do you play that in a browser, or do you? Anyways, let's find online video games. We'll just see if we can pop one open. Online video game emulator? I'm trying to get a specific idea of one going. Play retro games online. If this doesn't work in like 3 or 4 different clicks, I'm not going to do it. Yeah, Mega Man 4. How about that? Let's see if we can get this to work in 3 or 4 clicks. No, it says download something. Heck no, I'm not downloading anything. Okay, so forget that idea. But you have the idea. Running an emulation. These games, that kind of stuff, Mega Man and stuff like that, were written in the 80s for that kind of hardware. So they weren't expecting much. So nowadays, since our computers are 1,000 times faster than they were back then, an emulator can run them, can go ahead and run them. So we could do lots of cool stuff with Python. We can write games with it. But it's an interpreted language, meaning that it sits on top of a runtime engine. The shell. I'm going to stop using the word runtime engine, and I'm going to start calling it the shell. When we launch idle, it goes into the shell. It goes into the shell, right? And this is the same thing that runs our program. When we do a file new and we create a program, and then we finally run it, right? What happens is, well, why don't we wait until we get to the PowerPoint? So syntax. Syntax are the rules of the language, the order in which the things have to be written. How you add 1 to a number. There's lots of different ways to do that, right? If you have a variable called a is equal to 10, and you want to add 1 to it, this is like the most primitive way of doing it. When I say primitive, right, if you were going to write a programming language, you might do it like that. You have an algebraic expression here, and it calculates that expression, and it copies it over there. But that is something you do so often in programs that people make shortcuts for it as well. And when I say people, the people who design the programming languages. That means the same thing as this. Add 1 to A, store it back into A. And other people, other programming languages have done that. That means add 1 to A. Or maybe the plus plus goes in front of the A. And the syntax, this does not work. This does. So does this. Some languages require semicolons at the end of each line. You'd have to do A is equal to A plus 1, semicolon, like that. Some programs use curly braces to denote blocks of code. That's like C and Java. A lot of languages use curly braces. Python uses indentions. So if you write a loop, for example, in C or Java or something, it might look like this. While x is less than 10, print x, and something like that. That's kind of a C/Java style. And when you say C, it's also including all those variants of it, C++, C#, so on. Python, you would do it like this. While x less than 10, colon, and then you would tab over. Although in that language, in that editor, it's actually just 4 spaces rather than 8, so I'm going to do those by hand rather than hit the tab key. Print x, x plus equals 1. And that's the difference. The same code does the precise same stuff, but there are differences in the syntax. These languages require parentheses around that. It wouldn't break Python if you put the parentheses, but it does not require them. This one does. If you took the parentheses out, it doesn't work. Here's a colon here. There's no colon there. The colon tells Python that the next thing is going to be indented, and it's part of a code block. There's no colon here, but it knows that it's going to be indented because it's got a curly brace there. Indentation is critical in this language because it's how it knows that there's a code block. Indentation is not critical in this language because you have the curly braces. You could do this. Right? It's stupid looking, but the program would work just as well. I should make this a comment, though. A comment is something you put in your code that gets ignored by the computer. It's just for us to read. That's a C-style comment. Here's a Python-style comment. We could see that the same code looks considerably different, but it does the same thing. Ultimately, though, it doesn't look that different. Right? It's still a loop, and it's still got an output statement, right? It's still got a kind of an algebraic expression there, and it's still got variables, stuff like that, right? So, to make this code more complete, we would have to, here we're using a variable that was never defined. So, if it got to this part of the code, and we had never created a variable named x, it's not going to work. Code probably won't even compile. If you clicked run, it probably wouldn't even start running because we don't have a value for X. Just like if you tell somebody to go wash your car, but there's no car in the driveway, they're not going to be able to wash your car. It has to be a car in the driveway for that to work. So you always have to create a variable before you can use it. And you always have to put a value into it before you can compare it. This is a comparison statement, right? Are you less than something? Are you equal to something? That's a comparison statement. So in this language, you would declare a variable by putting a data type in front of it. You're going to say this is an integer, and an integer is a whole number. And I'm going to start it off at 0. Well, in Python, you don't have to declare your variables by giving it a data type. It assumes the data type. And by the way, everything I say, I'm going to repeat in a different form, and I'm going to repeat again in a third form. So it's not like everything I say in here, you're going to have memorized the first time. I just wanted to start to sink in, and then the next time I mention it to sink in more, and the third time I mention it, yeah, then it's locked in. So anyways, in this type of language, you do have to declare your variable before you can use it. In this one, you just put a value into it, and it already knows the data type. Oh, well, 0 kind of looks like an integer, so I'm going to make X an integer. We're not going to talk about these other languages very much. The book is full of examples of them. In fact, Python was not covered by the textbook until the 9th edition. Fortunately, there are examples, of Python in the book as well. We could teach the language even if the book never showed a single Python example. But thankfully, it hasn't, right? So that we can, we like for the book to more closely match what we're doing here. We'll be talking about Python 99% of the time. Why am I talking about other languages right now? I'm just trying to hone in on the idea of syntax. Syntax is important because if your program doesn't follow the correct syntax, it won't compile. Does that mean it's hard? No, it just means that once you learn the syntax, it's easy. I have learned that I always have to do this and that I cannot do this. Right? The variable has to be on this side of the equal sign. That's just a matter of syntax. And a million languages follow that syntax. I'm not sure how many languages there are that would support that syntax. I've never run across one. I won't say that there's not any. So once you see that and once you've typed it in a couple of times, you get the idea that the variable is always going to go on this side and the number or the value or the expression is always going to go on the other side of the equal side. So the left-hand side is the variable, the right-hand side is the data that gets copied into it. That's just a matter of syntax. This is good syntax. This is bad syntax. If you have this in your program, the program will not run. One of the things you got to fix before you upload it to me, right? So, rules governing word usage, the punctuation, whether you put a semicolon at the end of each line or not, or whether you have to put stuff inside of parentheses or not, or where you separate things by commas, when you use square braces rather than parentheses, all of that is syntax. And we will learn that as we go along. And it may seem like a lot at first, but that's why we type our code in during class as well. So that, I don't just sit up here and drone, for an hour and 15 minutes and then send you all off and you've never typed it before and you have to learn it, that part of it all at home. I want you to know the syntax before you actually do the homework. So mistakes in the language's usage are called syntax errors. We've talked about that. Don't turn in anything with syntax errors, or if you do turn it in, plan on revising it because you're not going to get credit for it. I always upload the notes from the end, at the end of the lecture, and so sometimes I do a little cut and pasting from the PowerPoint, but you should be looking at the PowerPoint as well as my notes when it's time to review. Alrighty, computer memory, right? I'm going to buy a computer and I want to put a lot of data on it, so I'm going to get a huge hard drive, right? Well, that's one kind of memory. That's not volatile memory. Volatile doesn't mean, oh, I'm angry, I'm going to explode. It just means that if you turn the power off the device, the memory's wiped out, right? You reset your phone, the applications are no longer running, right? Then you have to relaunch the applications in order to get stuff running. You turn your computer off, your game's no longer running. If you turn the computer off without saving your Word document, it's gone. That's RAM. RAM is volatile memory. It disappears when you turn the computer off. Non-volatile memory is permanent storage. Now, is it really permanent? Is this stuff going to be here 10 million years from now? Well, probably not, but it does last even after you turn the device off, right? You reset your iPad, you turn your computer off, you still have the hard drive, so you can reload your programs, you can reload your, re-access your term paper or whatever. So if something doesn't get stored to the hard drive, it's lost, right? So if you write an application, you may very well wind up writing it so that it can save to a file or load from a file, right? Because otherwise, it'd be uncool if every time I wanted to, create a resume, I had to type it in by scratch, right? All the way from the beginning, and then I send it to a printer, and then I close the program. Well, that's a drag, right? If I can save it to a file, and then come back later and load it from the file and make changes, that's infinitely better. So we will, at some point, be saving stuff to a disk, and then loading it from a disk. And what's the really cool, awesome way of doing that? Now they call it cloud-based computing. Cloud-based just means that the hard disk is stored on the internet, right? And so something gets saved on the internet rather than on your machine. Or maybe it gets mirrored there, like your photographs may all be uploaded to Google or Apple server or whatever. So, yeah. Non-volatile memory is the permanent memory. Random access memory contains everything that's going on at this point. And it's funny how little random RAM there is in these phones. We like buying terabyte-sized hard drives now for our desktops, and the laptops probably at least have 500 gigabytes, which is 1 billion bytes, and a terabyte is 1 trillion bytes. Phones probably only have, 1 or 2 gigabytes of RAM, in comparison. Whereas if you're, getting your game machine desktop going, you're probably installing 16 gigabytes, 16 times as much RAM. And the phones, the programs for them are kind of a miracle of optimization and efficiency, right? You can be a wasteful programmer when you're programming for laptops and desktops. These programs are huge. If you've ever looked to see how much RAM that Chrome is eating up on your computer, go to the task manager, see if we can figure this out. Okay, right now Chrome is only using, 3 million bytes. But if I kept using it, or if I did a lot more, it'd probably be using a gigabyte, And then all your other stuff is also using a lot of RAM at the same time. Phones do a real good job of swapping things out so that if you're not using the application at that time, it doesn't have anything in RAM involving it. It just writes its state out to its so-called hard drive, but phones don't have hard drives in it, right? They have some kind of flash memory in them. Same idea though. Just like laptops nowadays don't come with hard drives with spinning magnetic media, but they do have, some kind of solid state memory in them. Where was I going with that? Anyways, you tab from one application to another. It gets written out to memory in some way. Its state does. So that it's not sitting there running at the same time, right? So that, your text editor or your phone contact list or your whatever is not running at the same time as your internet browser. Now, sometimes things do have to run at the same time, right? You're listening to music and you're browsing the internet. You got to have two things going on at the same time. So the phone's going to juggle the fact that sometimes we're running two things at once and sometimes not. Now, laptops, desktops with its, buku huge endless amounts of RAM, not really, they don't care. You launch 20 programs, they're all running at the same time. And they can do something where they swap RAM out to disk, and they can use their hard drive as an extra source of RAM. It's called paging, but it's different than the way the phones do it. The phones and the tablets, they're very aggressive about swapping stuff in and out to keep the memory footprint of the programs that are currently running as small as possible, so that they don't have to spend extra money on installing, larger chips in the phone. Alrighty, so the compiler or the interpreter. That's what I was kind of talking about when I put here. Poor people watching this video, they don't get to see me drawing on the board. So I really don't draw too much on the board because I don't get this clear. And then the markers never work and so on. So anyways, there is compiling. And then there is interpreting. Compiling is when you take some source code, right? A is equal to 1, and then print A. And it turns it into an executable, a .exe file or a .app or something like that, right? And then you can give your friend or your customer or whatever just that executable. You don't give them the source code, right? They don't get to see that. You don't get to see the source code for your favorite game, most likely. That's highly valued intellectual property. An interpreter takes those lines of code, A equals 1, print A, right? It runs on the source code file. Right then and there. It doesn't create an executable. It doesn't create an app. It's just right on the fly. It runs first that line, and then it runs that line. So every time it runs, it has to reprocess this file. It does so on the fly. It's called interpreting it. Compiling it is taking this and changing all of the ones and zeros and ones and zeros, and that's what you give to your customer. That's what you run. Here, you always have to have the source file, right? If somebody else is going to run your Python game, you're going to give them Python. Well, I mean, you're going to give them your source file, and you're going to tell them to install Python. Now, it is possible to bundle a Python file with enough stuff that it can work as an executable. And it'd be kind of cool if we did that, but that's not the real point. The interpreted stuff happens on the fly. Each and every time you run it, it has to be turned into those ones and zeros, which are then executed, in the browser or, on your computer or whatever. That's the difference between the two. Compiling, you do it once, and then you can run this program 1,000,000 times. Interpreting happens every single time. And it's done by that emulator kind of thing I was telling you about, that runtime engine. So every time you want to run a Python program, it loads Python and then runs every line of your code. So, but in either case, the source code is getting changed into machine language. It's just that the compiler does it one time, and it makes an executable file. And then that file gets run over and over, and it never has to be compiled again until somebody wants to change it or make it work on another operating system. So the compiler, run once, make an exe, then that exe can be run over and over. And in that case, you don't distribute the source code. Now, when I say you don't distribute the source code, maybe you've heard of the idea of open software. Open software is when developers agree that they are going to share their code with each other, right? Software should be free, is one mantra, because if you write something really cool to run on your computer system, it'd be really nice, if somebody else could make it run on their computer system. And so there are places where people share code and stuff like that. On the other hand, people like to charge. Some people like to charge for their programming time, and so they don't make their software open source. Anyways, if you want open source software, you can usually get a hold of the source code for it. You could probably get a hold of the source code for Android, or at least big chunks of Android, because I believe it is an open source kind of thing. Now, the code that runs the iPhone is not open source. So you make it executable over and over. You don't distribute the source code, just the executable. Interpreted code runs every time you run the program, reading the source code each time. So you do distribute the source code. Running and executing are the same thing. There's always multiple terms. It's like terminating a program and killing the program and quitting the program, you know, all mean the same thing, except terminating or killing kind of implies that you're doing it not in the standard way, right? If I'm going to quit the program, I'll click the X. If I want to kill the program, I would load up a task manager, find it there, and kill it there, right? Here they're just calling it end. Okay, yet another synonym. You'll find a lot of places where different terms are used for the same thing. Hopefully they kind of sink in pretty quickly. Like you probably already knew that if you end a program, it's the same thing as stopping it, as killing it, as, you know, whatever. So, programs with syntax errors cannot execute. And then, along with syntax errors, there are logical errors. It produces the incorrect output, right? If you write a program that's supposed to do division, but instead it does multiplication, that's not a syntax error. It doesn't crash. It just gives you the wrong input. You type in 2 and 4, and you wanted to see 2 divided by 4 equals 0.5. Instead, it multiplies them, 8. Well, that's not cool. There can be more subtle logic errors as well. You know, people keep sending probes off to Mars, and it turns out that that's really not the easiest thing to do. A lot of Mars missions fail. Not so much recently, but that's because they spend billions and billions and billions of dollars, double and triple checking and everything. But for example, I know that at least one failed in the 80s because part of the code was expecting the units to be in English, right? Feet and pounds of thrust and stuff like that. And then another module was designed to send its output in metric. And you would think that someone would have noticed that before they sent it out there. So, you know, when it was supposed to land, you know, it instead just, you know, turned straight towards the planet, put on its thrusters, and it rammed into the planet. And whoops, there goes your $10 billion. Right, so that's a logic error. Some people categorize a third type of error. So we could say that there are syntax errors, which we have gone on enough. And in logic errors, program runs but produces the wrong output. Right, so your character blips through a wall when you're playing a game, right? Or it dies for no reason. Or the game hangs at a certain point. That would be a logic error. And then runtime error. And I don't recall if the text calls it something else or if they just group it under logic errors. But a runtime error is when the program gets to a state where it just simply cannot run any further because something's seriously wrong. It cannot save to that file because the file doesn't exist, or the disk is full, or you're accessing a drive letter that doesn't exist, or that directory is write protected. There can be any number of reasons why you can't write to a file. Well, if you don't handle that correctly, it can kill the program, right? Boom. You'd be really unhappy if you'd written an entire term paper and then just because you couldn't save to the file, your program quit and you lost your term paper. So generally, you try to program in such a way that runtime errors don't happen. You handle the state, right? Just like it'd be really annoying if every time the internet went down, you know, your Wi-Fi router was down for a moment, your browser crashed, right? It was gone. Instead, it's just supposed to sit there and display a message and let you run it again. It's supposed to be fail-safe. It's supposed to handle these things. A runtime error is when those things are not handled. So syntax errors stop the program from running to begin with. A logic error is when it runs but produces the wrong output. right? The thermostat turns the heater on when the temperature gets above 100 degrees rather than turning the AC on, and then logic error, that kind of thing. Logic errors can be bad news, like an X-ray device, a medical X-ray device that exposes you to 100 times as much radiation as it was supposed to deliver because of a programming error, right? That's real bad. People get sued, and people, died from stuff like that. Cars with logic errors. You step on the accelerator, but the computer inside it, or you step on the brake, but the computer inside it decides that you were stepping on the accelerator instead, and so the car goes vroom and crashes, right? Bad stuff. The logic of the computer program is the order in which the sequences, the instructions are run. So something like this. I'm not going to even write it in Python. So far I haven't had y'all write any Python. We may need to fix that, but this may be one of the few times we do a class where y'all not writing Python. So for example, input age. If age is less than 18, say you can't vote. Else, say, okay, you can vote. And then if age is less than 21, say, get out of the liquor store. Else, say, go ahead. That kind of stuff. This is the logic, because sometimes certain things are going to happen, and then other times other things are going to happen. And they're going to follow, they're going to happen in a specific order. Quite often it's top down, but if there's a loop, then it will repeat that stuff over and over and over. And so it's not always top down. And even when it's running top down, sometimes, certain statements get skipped. It's not going to print you can't vote and you can vote at the same time. One of those will be skipped because of that condition there. So that's the logic of the program, right? There's different ways of expressing the logic of a program. You can use flowcharts, for example, to map out the logic of the program. And so there will be places where it branches. The if statement will branch. It's supposed to go one way or the other. Eventually, the branches will hook back up, right? Because it ran this stuff. It did either one or the other, but then it ran this anyways. It didn't do this check. It didn't skip this check under any circumstances, right? It always does this check. So these two, this branch here, went back together. So if you were going to flowchart it, there'd be a diamond with an if statement, something involving 18, and one way it would print something, and then another way it would print something else, but then they have to join back up together so that you can then check to see if it's 21, right? That was our next check. And then if it's 21, it prints one thing, else it prints something else, right? And then they go back together, right? And that's the logic. Now I missed something. I missed the input step, so there should be an input step before that, right? And if I was going to make a flowchart, I wouldn't just draw the shapes, right? I'd fill in the details of what these blocks are, and then I'd put a little circle at the bottom that said stop, and a circle at the top that said start, right? But that's the idea of a flowchart. It's a map. This is a map of the same thing as the code. If I gave you this code, or this map, you could write this code, and vice versa. If I gave you this code, you could write this map. So logic can be expressed in multiple ways. And if you're working in a different programming language, again, the logic can be expressed in multiple ways. Just to give ourselves something to upload, let's go ahead and write a program like this. Now, we could have written this logic in such a way, well, we'll play with that once we get idle going. Go ahead and launch idle. And this is lecture B. Put your name up there. So if logics are also known as decision. If you feel like putting the date, that's cool. I always want you to put a comment block up at the top of your homework. I don't care so much about the in-class stuff, but why not put it there too? Especially if you see me do it. Sometimes I'll forget. All right, let's get somebody age. Let's ask for their age. Print, all lowercase, open parentheses, shift 9. I'm going to use double quotes, but you can use single quotes. What is your age? Now we have to get the input. So age is equal to input, parentheses in parentheses. Then we have to turn it into a number. It's not a number yet. They could have typed in anything, right? They could have typed in, you know, I hate programming. You can't do math on that phrase. We have to turn it into a number. If they type in the wrong thing, if they type in I hate programming and we try to convert it to a number, we'll get a runtime error, right? Because we could not turn I hate programming into a real number. So that's going to be the next thing we do. Age is equal to float, all lowercase, parentheses age. All right, now we have a number. I think I'm going to add some comments, which you don't have to do, but this is the input stage. And this is some data processing stage. Just kind of remind ourselves of what we said, you know. We usually gather some input, we usually do something with that input, and then we usually display some output. Now, we're not going to just display one piece of output because we're going to have some if statements. All right, what else is age dependent besides voting and alcohol or other prohibited substances? How about like going to grade school, right? Yeah, you have to be at least 6 years old. So, if age is less than 6, colon, and I'm sorry, whenever I read these things off, I always say the word is, but you don't type it, right? It's not if age is less than 6. It's just if age less than 6, colon, print, quote, too young for school. We're going to pretend there's no such thing as preschool or whatever. And then next time, print, parentheses, quote, come back later, in parentheses. I'm going to go ahead and test it at this point because if there's a syntax error, I want to catch it early. You know, I could write 20 pages of code before I run it. That's not really the best idea. So save as, I'm going to call this lecture B, or maybe just B. How about lecture B? It drives me up the wall that there's no favorites folder here that I can save to. Did I already mention that? Maybe I didn't mention it in this class. Maybe I did last month. Where's my favorites? If any of y'all know how to enable that. I think it's been disabled by the admin, which is insane. Okay, I guess I did say that to y'all. I better actually ask them about it so I won't complain every single time we do it. Alrighty. Then, so I saved it, right? But if I had just run it, it would have asked me if I wanted to save it. So run module, source code must be saved. It's not going to run because I typed in if. And that's going to be a syntax error, so I'm going to go and delete that and then run it again. What is your age? I am 4. Too young for school. Come back later. I'm going to run it again. Programmers always run their program to make it work, but they don't test it to see if they can make it fail. Right? What happens if it's not supposed to print that? Like what if I type in 16? It doesn't say anything. Maybe that's a failure state. Maybe not. Maybe I don't care, right? But that's a decision you need to make, and you need to have run it both ways. So anytime this is a decision block in your code, you need to try both ways. You're going to try to see whether if age less than 6 is true, and you're going to try it again to see if age less than 6 is false, and see how it works either way. Because it might crash if you enter one piece of data, and it might not crash if you enter another way. So like I said, programmers usually run their program with the right data. They want to prove that it works, and then you wind up having a testing department that tries to break your code. And those groups of people hate each other. Right, I'm kidding. All right, I'm not going to put an else on that one because, But how about, let's do the voting one. If age is less than 18, and random side copy, I think if you're old enough to vote, you ought to be old enough to smoke and drink and stuff like that. Even though I understand the reason for raising the, Yes, sir.
I got a traceback error here.
All right. I'll be right back there. I'm going to add this first line here so that other people can type in, then I'll come back there. So if age is less than 18, I'm going to say too young to vote. End quote in parentheses. So I'm going to add one more condition to this. If age is greater than or equal to 18, colon, print, you can vote, exclamation mark, end quote, in parentheses. And now I'm going to test it again. Run module. What is my age? And again, I'm going to test it with multiple inputs. Well, I've already done the less than 6 and greater than 6, so I'm not going to test that this time. But I'm going to see what it does if I'm less than 18 or greater than 18. Well, you know what? 1 is certainly less than 6 and less than 18, so why not just choose 1? I'm too young for school, and I'm too young to vote. All right, but I'm going to try it again. You always want to test your edge cases. Your edge cases are right on the dividing line. 18 is our dividing line. And I'll show you what I mean. If I make this greater than, rather than greater than or equal to, the logic is now broken. But I may not notice it first, right? If I'm 16, I'm too young to vote. What if I am 19, right? Perfect, I can vote. So I'm confident that the program works, but it's not going to work. Why? Because what happens if I type in 18? It doesn't make a decision one way or the other. So that's a logic error. But I may not have caught it if I hadn't tested the edge case, if I hadn't tested the, the boundary. So I would need to come back and I would need to modify that to be greater than or equal to 18. And then I could test it both ways and it would work. Now, one thing that frustrates people is after they run the program, like if they get an error, they want to just rerun it immediately, right? I want to be able to type a 1. And, oh no, you have to rerun the program each time. By the time you finally get the red text error, the program has stopped running. And so that's just it. You have to come back here and rerun it. A lot of times people sit there at the shell thinking that they can, keep going somehow. Well, you can keep going if you've written the program in such a way to handle the error, but we haven't. All right, so to clean up the logic, I'm going to change this to use an else statement. Else colon, and then I'm going to delete that line, or at least comment it out. Commenting out means that the computer would ignore it, but it's cleaner if I completely delete it. Now it'll work the same way. So you might run it, type in something that's 18 or greater to make sure that we get to that message, you can vote. Be right there. So I'm going to type in 18, my edge case, and it says that I can vote. What if you accidentally close your application? Here's something that's kind of annoying. You go, oh, well, no problem. I'll just go find where I saved it. And I'm going to double click on it. And it does something, certainly not what I wanted it to do. So you actually have to open idle and then open it inside of idle. Fastest way to do that is just once you get into idle, do File, Recent Files, and grab it from there. But that'll be really frustrating if you download, you know, something, your in-class work at home, and all you have is your PY script. Just remember, you can launch idle first. Now, you probably can right-click on it and do open with idle, but I'm not seeing that there. Right? So that's annoying. Go into idle, then open the PY file. It's even worse in PyCharm, where you have to open PyCharm, and then you have to open the project, and then add that file to the project. All right. Anybody stuck on getting it to do the driver's license check?
Oh, I did pilot's license.
Whichever. Yeah. 16. Starship, my captain's license. Apparently Kirk's like 18 years old in the movies. I don't know about that. Why are they all the same age? They weren't in the TV show. Pardon me? From now on, just the code. Just the code, yeah. But let me make a Dropbox for it because we're entering our screenshot for homework, or screenshot and code for homework, but just the code for the in-class assignments because that takes a little bit of time and y'all are on, you know, wanting to get out of here.
So we run module, right?
Yeah. All right, so B, what is this? This is the age program.
You want to save it as an age program?
You don't need to save it as age, just upload it into the B Dropbox when you're ready.
Okay, I'm saying.
You don't need to rename it. It's cool. You don't need to do a save as. Just give me the B program, whatever you called it. You can rename it if you want, but you see that I labeled the folder B, so just stick your B program there. Yes.
So, is this correct? So I put in my neighbor's slide, so it popped up all of the.
Right. And so how about doing something between two of those, like 17? So go ahead and run it again. Yeah, you wish you could do it from this window, but you got to go to that window. So just hit run or F5 again, run module again. Try 17 because that's between the driving age and the voting age. Yep, that works. So a good piece of data to test is 17 because that's between voting and driving. Exactly, that's what I was talking about. Once you close idle and you try to open it like that, it doesn't work. You have to close idle again and then get to it from there. So if it was closed, you would just do file, open, reset. Right. And then you can get to it like that. I wish you could double click, but it's going to work for me because I know it's just going to work with it. Right. Right. Yeah, I've reconfigured my personal machine to not launch that WinPython thing, so it instead loads it up into the editor. Yep, that's it. So once you get your file there, we're all good.
Okay, so I just ran it, saved it.
So you're going to come over here.
And I just need to start answering the question.
Yeah, let's answer our question.
Okay.
Try 17.
17. Enter.
Yep. So we are too young to vote, but we're not too young to get our pilot's license. What age do you? Yeah. That's cool. That's cool. So try something between 18 and 25. Run it again like 21.
Okay, so
I wish you could run it from here. I wish you could type in, but you got to actually go back over here and run it again. You got to run the module a second time.
So I need to do the if.
Nope, just run it again. You're testing it with new data.
Run.
Now try it like with 21. You should say you can vote, but not fly.
You can't vote. Too young to get pilots.
Right. And then if you ran it with something greater than 25, it'd say you can vote and you can do your license as well.
So it's okay then, huh?
Yep, it's all good. So that's what you're gonna find your PY file and put it into the B folder.
You want both of these, so.
There is no both. There's only one PY file. Unless you did a save as, in which case, sure.
Yeah, I need to save that.
Yeah, that's cool. That's cool.
it'll automatically create the
Yes.
I don't know if you have very many female students, but if you do, there's a workshop that Teklahoma is doing
Oh, cool.
in March, and it's like Ruby on Rails,
Ooh.
and I like show you how to do
I'd like to
stuff.
take that.
Yeah, it's only for women, but you can
Oh.
totally be a volunteer and you can help people do it.
I can't turn it. Could you email that to me?
for sure.
Because I'd love to post it.
Yeah.
And I'll tell people to wear a wig. And no, I'm kidding. I'm
Right.
kidding. Okay, that is cool. And yeah, I love taking care of the female students. So thank you for mentioning that.
I can't see where I stay.
I'm going to tell you why. The thing is, how I got around that is I removed everything up home. It just said else. But if you like seeing that expression there, you can say L with try to change the else if you just change the SC. SC to IF. Same thing there, yeah. But what you really want to do is you just want to delete the condition. So just make it say else, colon. Delete the whole line and make it say else, colon. I showed you one way and then I tricked you up by changing it to string. Like that. If that's a colon.
Oh boy, oh boy, oh boy.
Don't worry about it. Yeah, I'm just going to delete all the rest.
Tense.
Yeah, that colon. And when I say everything, I mean on the same line. Okay. Yeah. Yeah, that's cool. That's cool. Yeah. That's cool. Okay, that's what it's supposed to do. Okay, but if you like changing your conditions like that, that's called a change if. What you would do is change that if to add the letters EL from it. From the I. Yeah, EL. And that just means else in. So, okay, right. And then that way you can do one check and then another check and then another check. It's like saying if A, else if B, else if C. And it'll work the same way. Yeah. Okay. Okay. What you think? Did you find your files?
Yeah, I'm putting them on the desktop.
Good deal.
And it looks like they just replaced one with the other, so they're the same anyways.